Hello, everyone. Anybody have any questions while we're getting started? Got you, Jared, no problem. Anybody else have anything? All right. So last time, if I'm not mistaken, we started into chapter 6. Let me double check that real quick. Because I can, I got superpowers, all that good stuff. That's the last meeting. No, the last meeting we didn't start. That's right. We just finished chapter 5. I did the inclined planes and all that good stuff. Go ahead and check that. Well, we're starting gravitation tonight, and luckily that's what I prepared for, so that works okay. What I want to double check though is what did I do, because I offered one of my other classes an extra credit the very first class. I want to make sure I do that same thing. Yes, I'll tell you that. Okay, so I told you a story about Newton and how he sort of was sent home because of the plague, and that he didn't really waste his time very much. He made the fundamental laws of classical physics as we know them. He wrote over 500,000 words on optics, over 500,000 words on the New Testament, and one of the other things he did was discovered a law of gravity. And the way the Principia reads is basically, he says he was sitting under an apple tree. His mother owned an apple orchard. He was sitting under an apple tree when he looked up and realized how the moon was just like an apple. And what he meant by that was when you look up at an apple, you know that it's eventually going to fall. And it's going to fall as a result of getting so succulent, basically, or so moist that its weight exceeds its spin strength, and then it falls to the ground. What he was reasoning is whatever's making the apple fall to the ground is the same thing that makes the moon accelerate towards the center of the Earth, because in order for an object to go in orbit, it has to be following a circular or elliptical path, which we know now is elliptical thanks to Kepler's laws. But in order to do that, you have to have a centripetal acceleration. That means you have to have a force pointing towards the center. And he said, I think it's that. Well, that was the big moment. He had actually studied optics so much that he knew that the intensity of light fell off as 1 over the distance squared. And because of that, he said, well, maybe this force of gravity basically falls like 1 over r squared. And then he did some quick calculations, which I'll show you in a second, and he got it exactly right. So let me start off by showing you that. So you guys learned about the centripetal acceleration. Him, having invented the calculus, had of course came up with this formula as well, by means other than the calculus as well, but also by the calculus. And that is the acceleration centripetal required to keep something in a circular orbit is v squared over r. And of course, what he knew was one thing that was impressive was he realized that an object like an apple is essentially the Earth radius from the center of the Earth. So he said, well, we know at r equals r of the Earth that a is equal to 9.80 meters per second. And then he said, well, if this obeys a 1 over r squared law, then then at r equals 60 Earth radii, which he knew from the center of the Earth to the center of the moon, this was the distance. He knew that then the acceleration due to gravity out there should be 9.80 divided by 60 squared. Well, when you do that calculation, you do 9.8 divided by 3600, that's what 60 squared is, and you get 2.72 times 10 to the negative third meters per second every second. So 0.0272 meters per second per second. All right, well, what's the acceleration that the moon has? Well, he knew the moon basically took a month to circle the Earth. So he knew the period of the moon, and he knew that, for instance, the radius of the Earth, he knew that figure as well. And since he knows R in terms of the radius of the Earth, he could easily calculate what V and R was. So he said V was equal to the circumference of the moon's orbit, which is 60 Earth radii in radius. And then he divided that by the period. And of course, the period for the moon was 27.322 days. And he probably knew it more like 27.3 days. We'll say that roughly. Well, that is also dependent on the fact that one day is equal to 24 hours, and that 24 hour that that converts it to hours from days, and that one day, or 365 days, excuse me. Did I do that? Yeah, 365 days is equal to 1 year. That's not what I wanted. Sorry about that. I'm trying to convert to seconds. What am I thinking? I'll erase all this and start over with a little bit more room to give myself so it won't be quite so crowded. So it's actually, I forgot the number. The number was 27.3 days. Now I need to convert from days to hours, and I know that one day is equal to 24 hours, and then I need to convert from hours to second, and then I know that 1 hour is equal to 3,600 seconds. Sorry about that. That was what I was trying to write, but I got confused and started converting it to a year for some reason. Okay. So anyways, I'm going to do that math. I'll say that is 2 times 3.14159 times 60 times the radius of the Earth, and the radius of the Earth is 6.38. Times 10 to the 6th meters. 10 to the 6 kilometers, excuse me. Yes, 10 to the 6 meters, 10 to the 3rd kilometers. And then I divide that, of course, by all that figure, 27 times 24 times 3,600. And that should give me 6.38 e to the 6 divided by parentheses 27.3 times 24 times 3,600, all in the denominator. So I use parentheses. And that should be the velocity. The velocity turns out to be 1.0197 times 10 to the 3rd meters per second, which just gives you a good idea. I just wanted to let you know what that velocity was roughly. So now we can say AC is equal to V squared, which is at 1.01, which really we only use 3 sig figs, so those two are extras. 1.0197 times 10 to the 3rd meters per second. I'm going to square that and divide it by 60 Earth radii again, which would be 6.38 times 10 to the 6th meters. And when I do that, I'm going to square that and then divide the answer by parentheses 60 times 6.38 e to the 6. And I get 0.0272 meters per second per second. So at that instant, He knew that the law of gravity was in fact a 1/r² law. And in fact, he knew exactly what caused the planets to orbit the sun and what caused the moon to orbit the earth and what caused any of the satellites to orbit their planets. For instance, we know about the Galilean moons and so on and so forth. And in fact, what he conjectured was that there was a law of gravity that was always attractive. It gave a force F, whose magnitude was given by G times M1 times M2 over R², where M1 and M2 are the masses of two objects. G is a gravitational constant, and R is the distance between, if they're point masses, it's the distance between the points. If they're actual full-size masses, then it's the distance between the centers of mass. And this constant G is equal to 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. So that was the law of gravity. What you see is that it's proportional to the mass. It's also proportional to the other mass. So it's proportional to the product of the masses. So if you double one of the masses, for instance, you replace Earth with something twice as heavy as Earth, then the force will get twice as big. If you replace the Earth with something twice as heavy as the Earth and the sun with something 3 times as heavy as the sun, then you're going to get 2 times 3 or 6 times the gravitational force. And it's inversely proportional to the square of the distance between them. So if the sun-Earth distance were doubled, then the force would go down by a factor of 4. If it was tripled, it'd go down by a factor of 9. If it's quadrupled, it'd go down by a factor of 16. Now, this is amazing that it happens to fit such a straightforward, simple mathematical law, but it turns out that must mean something really serious, because when Einstein became famous, they asked him, Professor Einstein, what do you think about ESP and telekinesis and things like that? ESP, your ability to read other people's minds and stuff like that. He said, if you show me a base of 1/r² law, then I'll believe it. Okay. Well, they've never been able to show that. So yes, Einstein never believed it. But it also turns out to be the same thing for electricity. In fact, the force for electricity is called the Coulomb force. And that's actually equal to K. Q1 instead of M1, it's a charge 1. Q2 instead of M2, it's a charge 2 over R². And here's the kicker. The K is equal to 8.99 times 10 to the positive 9. And that's Newton's meters squared per Coulomb squared instead of kilograms squared. So you can see, just by comparing these two, you can sort of automatically say, well, clearly this force, the Coulomb force, is going to be 1 with 20 zeros after it, larger than the gravitational force, but it's even worse than that. So for instance, if you realize that the electron and the proton have the same magnitude of charges, it's equal to 1.602 times 10 to the negative 19th coulombs. If you realize that, then you can do a calculation to find out what is the Coulomb force divided by the gravity force for the electron and proton in the Bohr hydrogen atom. So in that scenario, I got to tell you some stuff. So this is what you're going to be able to do for extra credit. If I remember correctly, I think the figure comes out to like 10 to the, well, like 1 with 43 or 44 zeros after it, put it that way. Okay. What you'll need to know, and you can look these up on your own, but I won't give them to you anyways. The mass of the electron is 9.109 times 10 to the negative 31st kilograms. And the mass of the proton is 1.67, I believe 1.6703, 1.67, yeah, 673, that's what it is. 1.673 times 10 to the negative 27th kilograms. So that one's negative 31. This is 10 to the negative 27. And of course, the Bohr radius, which I should be able to give you, is something along the order of 5.29. Let me actually look that up for you real quick. The Bohr radius is how far they are apart from each other. And that is 5.292 times 10 to the negative 11th. So the Bohr radius is the radius that Bohr predicted for the hydrogen atom's innermost orbit to have. It's often given the symbol A0, and it's 5.292 times 10 to the 11th meters. Okay. So what you're going to do is ignore the signs when you put in these formulas, just take them as both positive. You're going to calculate this force, you're going to calculate that force, and then you're going to divide this force by that force. And actually, if you're smart, you'll do it all symbolically, so you won't have to put the same stuff in over and over again. And you'll get just a value. I want you to round that to the nearest power of 10. And this is your extra credit. Okay. And that's going to count basically as an extra credit in terms of your conceptual homework. So for instance, if I told you I was going to drop one of your lowest conceptual homework grades, now I'd drop 2 instead if you did that. Okay. Any questions on that? So it's a straightforward calculation, as you can tell. I'm going to give you some ideas of how straightforward it is just by doing some calculations myself. So the main thing to remember is this Coulomb force, this gravitational force is always attractive. So if you want to find the force on N2, you're going to draw a line from the center of mass of N2 to the center of mass of N1 and point an arrow along that line towards M1, and that'll be the direction of the force. If you want to find the force on M1, you're going to draw a line between the two again, but that time it's going to be pulling it towards M2, so the vector should point along M2. Okay. So that's how you're going to do that. Does anybody have any questions about that? Does it make any sense or anything like that? All right, I got a couple people who came in or trying to come in. Let me let them in right quick. So that's how Newton more or less discovered the laws of gravity. And in fact, he went on with that law of gravity, he was able to make sense of Kepler's laws. And Kepler's laws, I'm not going to write them out in word form here. I'm going to say them to you and explain them to you. And it's Kepler's laws of planetary motion that actually turn out to be right for all planets, not just our sun. So his first law of planetary motion said that the planets orbit the sun in elliptical orbits with the sun at one foci. Okay, so you know that you can make a circle by putting a nail on a piece of plywood, say, and then tying a string to it and tying a pin to the other end of the string, pulling it tight and trying to keep it tight, and it'll come back and make a circle. Well, with an ellipse, you put 2 nails in the plywood and you connect them with a piece of string that's longer than the distance between it. And then you pull it taut. And when you do that, it traces out a shape like this. And that's, well, sort of like this, not quite that ugly, but still. This is called the major axis. And half of it is called A, the semi-major axis. These are the focal points, plural of which is foci. Okay, now this from here to here, that's the minor axis. Now this is the actual axis, but this is the distance called the minor axis. And as you might suspect, this is the semi-minor axis, but we hardly ever use that. Okay. So that was a big deal because Aristotle had taught us that the heavens were perfect, and it was obvious to everyone that since the heavens are perfect, the only perfect shape is a sphere, therefore everything in the heavens must be spherical. So even the planets were imagined to be on crystalline spheres, and tracing out shapes in the sky that were circles, because a circle is like a two-dimensional representation of a sphere. So everything was supposed to be exactly a circle slash sphere. And him saying it's an ellipse was really anathema, because an ellipse is more or less a bastardized circle. Well, what Newton was able to show was, by using his law of gravity, he was able to show that there's only two forces in nature that can create a stable orbit. One of them is a 1/r² law, and the other one is Hooke's law, which says that force equals some constant times x. Those are the only two that make stable orbits. So Newton was able to prove that. And he was able to prove that, in fact, the only orbits that can happen were conic sections. So if you've ever been to those junkyards or gas stations that have those paper cups that are shaped like cones, now imagine two of those cone-shaped cups stuck tail to tail like this, but going on forever. Okay, that is a conic, as we're talking about. If I were to slice it this way, say, it would trace out a circle, or excuse me, trace out a shape that's actually an ellipse. If I sliced it this way, which is perpendicular to the axis, it would trace out a perfect circle. If I sliced it this way, it would trace out a hyperbola. That's what those two sheets are. And if I sliced it this way, it would trace out a parabola. So those are the possible shapes that you can have of orbits: hyperbolic, parabolic, elliptical, and circular. Okay, so that was Kepler's first law, is that the planets makes elliptical orbits with the sun at one focal point. There's nothing special in the other one, by the way. And his second law was that when you draw that ellipse, like such, and here's the sun down here, if it takes you 30 days, so day 1 to day 30, if it takes you 30 days to go that far, then you'll find out later that it'll also take 30 days to go this far. Then what you know is A1 is equal to A2. In other words, if you imagine a crappy elliptical pizza, and you have to cut it where all the lines cross here at where the sun is, okay? If you want the same amount of cheese on one slice, this slice is going to have to be short but wide. A slice over this end is going to have to be long but skinny. And that's basically what he's saying, is that the planets sweep out equal areas in equal time. In equal time. That's the second law. Okay. Newton was able to show that, and in fact, we eventually, and he was able to figure out that basically something equivalent to angular momentum was being conserved. Okay, we know that's the reason that this law is true now. It's just conservation of angular momentum, which we haven't learned about yet. Okay, now the third law, Kepler gave it to us, but without any rhyme or reason to it. He just realized that the square of the period was equal to the cube of the semi-major axis. So what he said was t squared is proportional to a cubed. Remember, I said a was that semi-major axis. It's also more or less the average distance, because you can tell when the sun is here and the earth is here. That's called perigee, or perihelion, sorry. Perihelion. And when it's here, it's called aphelion. So if you take this distance, which is the closest it is to the sun, and add it to this distance, which is as farthest as it is from the sun, and then divide that by 2, you'd get basically an average of the distance between the Earth and the sun. And in that sense, if you added this distance plus this distance, you see you're going to get the major axis. Now, if you divide that by 2, you now get the semi-major axis. So that's why it's that. And basically all he did was look for all the different powers of T and A that ultimately gave you a straight line for all the planets. And that happened when T was squared and A was cubed. Okay. Not only that, now that we've studied centripetal acceleration, we know that G, M, Sun, M, Earth, these are the symbols for the sun and the Earth. That's the sun, for obvious reasons, it's a circle with a dot in the middle. And this is the Earth, is a circle with a plus sign in the middle, over R squared, where R is the distance between the sun and the Earth, which we define as 1 astronomical unit. We know that that's the only force acting on the Earth to keep it in orbit around the sun. And if we assume for a second that it's a circular orbit, because it turns out, even though he's right, if you drew 2 equally sized orbits, one that was perfectly circular and one that was an exact replica of the Earth's, without a lot of detailed, time-consuming measuring, you would not be able to tell which one's the actual circle and which one's the actual ellipse. That's how close to a circle they are. So going on that, we're going to say, well, we know that Newton's second law tells us this has got to be equal to mass of the Earth, velocity squared over R squared, or excuse me, over R, not R squared. So you can see we have some way of actually doing this, assuming is my ink eraser still finally out? Yeah, okay. So you can see from this that first, the mass of the Earth is going to cancel out. You can also see that one of the R's is going to cancel out. But knowing that V is equal to 2 pi R over T also gives you that G M sun over R is equal to 4 pi squared R squared. I should use the same R. So I switched to big R for some reason. So I'll just switch to big R and run with it. Big R squared over T squared. Okay. So now what you can do is when you solve for T squared, you'll get T squared is equal to 4 pi squared over G times the mass of the sun times what we called R cubed, because this times this gives us the R cubed, because this times this gives us the R cubed. So this is more or less a somewhat of a proof of Kepler's third law. We just bypass the complexities of dealing with it being a circular orbit instead of an elliptical orbit instead of a circular orbit. But when you do the same calculation properly with an ellipse, the only thing that really happens is instead of just mass of the sun, you get parentheses mass of the sun plus mass of the Earth, and you still get the same formula, but A instead of R. So that's really what Kepler's third law is. And it does actually apply to all planets, but of course, this part's what differs from one star to the next, or from a planet to a star. So if you're talking about the moons orbiting Jupiter, then this becomes 4 pi squared over G times the mass of Jupiter. And therefore, it's still T squared is proportional to R cubed, but the constant's different. So any questions on that? So those are the big facts that you need to take from this chapter. Now let's go ahead and do some actual calculations. Let's calculate, for instance, the attractive force between the sun and, let's say, the Earth. And let's do the attractive force between the moon and the Earth. So if you take the force of gravity between, let's say, the Earth and the sun, then you're going to have to, of course, look up what the mass of the Earth is and the mass of the sun and all that good stuff. That's not that big a deal. All we have to do is I'll write the units this first time, but I'll ignore them from there on out. You should do them on your tests and homework just to make sure you understand how they work out. But this is going to be 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared times, now I need the mass of the Earth, and the mass of the Earth is 5.98 times 10 to the 24th kilograms, times the mass of the sun, which is 1.99 times 10 to the 30th kilograms. It's like 200,000 or 500,000 times the mass of this Earth, if that tells you anything about how big it is. And then, of course, the distance between the sun and the moon is what's called 1 AU, 1 astronomical unit, and that's 1.496 times 10 to the 11th meters. So I'll put 1.496 times 10 to the 11th meters. You can see that that meter squared is going to cancel out with that. These kilograms squared is going to cancel out with that. And I should just get the newtons at the end. And in fact, when I do that, I get 35.47. I use 3 sig figs essentially on everything. So I really shouldn't take it any farther than 1 decimal place. 35.47 times 10 to the 21 newtons is what I get. That's the force that the sun applies to the Earth. If you want to calculate the force that the moon applies to the Earth, then I'm just going to say F Earth, and the symbol for the moon is just that little left-sided crescent, which should technically be a waxing crescent. That's going to be 6.67 times 10 to the negative 11th. Again, leaving off the units like I told you I would. 5.98 times 10 to the 24, and then 7.35 times 10 to the 22. All of this over basically 384, 384 million meters basically. So 3.84 times 10 to the 8th meters, and that's going to be squared. When you do this math, it turns out you get 198.8, that's 1 extra digit, times 10 to the 18th newtons. Any questions on that? So you can see they're comparable. The biggest difference, though, is the force of the sun on the Earth as a tidal force. In other words, how much more is the force on this side of the Earth, closest to the sun, than the far side of the Earth, farthest from the sun? And the same thing for the moon. And then you find in that case that it's reversed, because that difference in forces, that tidal force, turns out to be a 1/r³ law. So you end up getting that the force the moon applies to our tides is about twice as big as the force the sun applies to our tides. So any questions on that? There's another neat calculation I like to do with gravity, and this one's actually comes from the original Cosmos series. I'm hoping all of y'all have seen the Cosmos series by Neil deGrasse Tyson, but the original one was based on the book by Carl Sagan called Cosmos, and he's more or less just giving everybody a rundown of what we've learned in big science. And I want to say it was a 7 or 14 hours, I can't remember. I had it in VHS and I've got it in DVD now, but it's a really good program. It actually has more information in it and more details than Neil deGrasse Tyson's does, but it's really antiquated in terms of the technology, but still really nice. Anyways, in that argument or in that video, one of the episodes, he's talking about the dangers of pseudoscience, which is really pressing right now in America. But one of the dangers of pseudoscience, in his case, he was talking about astrology, is that people believe things that aren't true, which is usually pretty harmless until you start making major decisions or something like that based on stuff like that. It can be quite reckless. In fact, we've had presidents and first ladies that consulted the stars to make decisions about important government things and stuff like that. So that's kind of sad. But what he wanted to do is say, okay, well, let's imagine that astrology really is a science. It's not, it's a pseudoscience, which means not a science. Okay. But if it was, then there should be some kind of mechanism, something that connects us to the planets. For instance, if whatever constellation the sun is in at the time of your birth, that's a really big deal. For instance, if the Mars is in your birth constellation at birth, and that's a big deal. Little stuff like that. So what he argued was, well, the only thing we can imagine that could have any relationship to the planets is the force of gravity. And it turns out, he said, that the force of gravity between Mars and a baby at the time the baby's born is less than the force of gravity between the baby and the obstetrician delivering the baby. So I like to do that calculation just to show everyone. So let's say the force on the baby as a result of Mars, and this is the symbol for Mars. Y'all might recognize this as something familiar. That's going to be equal to 6.67 times 10 to the negative 11. I'm going to assume the baby is in fact 3 kilograms, and I'll just do 1 sig fig. That's cool enough. I'm going to say the baby is 3 kilograms. Of course, Mars has a weight all by itself, and Mars's weight is quite a bit smaller than the Earth's weight. It's 0.624 or 42 times 10 to the 22 kilograms. Now, the way it works, though, the sun is here. This is Earth's orbit. And then Mars's orbit is outside of that. And in order for Mars to be the closest, they have to be in opposition. And in fact, this is that time of year where you get an email just about every year saying that the Mars is going to be so big, it's going to be bigger than the full moon in the night sky. That's the origin of it. It is going to be bigger, but it's not as big, anywhere near as big as the full moon. That's just a misinterpretation of something. But the distance from here to here is 1 AU, but the distance from here to Mars is 1.52 AU. So the closest Earth and Mars come is when Mars has the best chance of affecting the baby. So we're going to use that distance, and that turns out to be 0.52 astronomical units. And then we do times 1.496 times 10 to the 11th meters per 1 AU and square that. Okay. That will give us the force that Mars is actually applying to the baby when it's born. It turns out that force is about 21.2 times 10 to the negative 9th newtons. So Newton's a pretty small unit anyways, but now we're talking 10 to the negative 9th. So that's a real small amount. Now, if you want to calculate the force on the baby due to the obstetrician, then I'll go 6.67 times 10 to the negative 11th. And this time I'm going to say, well, the baby still weighs 3 kilograms, but I'll assume the doctor weighs 80 kilograms. Okay. So that's, an average size doctor. It's not a fat guy like me who weigh, over 100 kilograms. But their distance is only going to be about 0.5 meter. Because I'm imagining the baby still being in the womb, the obstetrician sitting down low, at least a foot or so away from the where the baby's coming from, which I don't want to go any further than that. And anyway, so that's a pretty good approximation, because that's about how far he's going to be when the baby starts to come out. Eventually, of course, he's going to be touching it, and I don't want to use 0 because that would be an infinite force. So if we use about 0.5 meter, it turns out that this gives you about 64.0 times 10 to the negative 9 newtons. So you can see that it's more than 3 times larger a force of gravity on the baby due to the obstetrician than there is due to the actual planet Mars. Kind of neat, huh? So Carl Sagan was right, which, duh, right? All right, any questions on that? Okay, so something else neat that we should know is we studied balls in free fall, and we learned that they actually accelerated at a rate of A equal to G. And from that, we were able to conclude that weight was equal to M times G. Well, now I can tell you, since we know the formula of gravity, we know that this mg is caused by gravity. So in fact, that mg is equal to g times your mass times the mass of the Earth divided by, you're essentially on the surface of the Earth, and the surface of the Earth is really quite smooth. In fact, if you go from the deep grooves in a basketball up to the top of the dimples on the basketball, that difference in height from the bottom of the groove to the top of a dimple, that difference in height is much bigger than the difference in heights of Mount Everest to the Mariana Trench compared to the radii of the bodies. In other words, the Earth is a better sphere than a basketball is. Okay, so because of that, we know that we're essentially on the radius of the Earth. So I'll put our Earth here squared. Immediately, you can see that the mass of us disappears, and we get that G evidently is supposed to be the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. If you put that in, you will find that it is 9.80 meters per second every second. So go ahead and try it. 6.67 times 10 to the negative 11th, and that's newtons meters squared per kilogram squared, times the mass of the Earth. We knew that the mass of the Earth was 5.98 times 10 to the 24th kilograms. And then we knew that the radius of the Earth was, I think we didn't I do that 6 point, yeah, the radius of the Earth should be about 6 point, it's about 6 times 10 to the 6 meters, if I remember correctly. Let me double check. Yes, 6.38 times 10 to the 6 meters. Rule of thumb that we use, that's why I remembered, is it's roughly 6 to the 6th. So that helps us a little bit. So now I have those figures in. Let's compute them and see if we get what we thought, what I claimed. 6.67 e to the negative 11 times 5.98 e to the 24 divided by parentheses 6.38 e to the 6 squared. And that gives me 9.799 meter per second per second. And you can see basically it turns out to be a Newton per kilogram. So Newton per kilogram is a meter per second per second. Any questions on that? Now we've got another thing we can do. Let's see how much G changes at the highest place on Earth and the lowest place on Earth. So G at Mount Everest, okay, that would actually be 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. Now this time it's going to be 6.38 times 10 to the 6 meters plus the height of Mount Everest. And the height of Mount Everest, if you read Into Thin Air, you probably have this memorized, is 29,032 feet. Actually, it's different. It was, I think they said 35 feet is what it said in that, because we had a major earthquake and the heights changed significantly in that major earthquake. So it's now 29,032 feet. But in meters, that turns out to be 8,848.95 meters. So we're going to add those two, of course, and then square it. When I do that calculation, I can see 6.67 e to the negative 11 times 5.9, or excuse me, 5.98 e to the 24 divided by parentheses 6.38 e to the 6 plus 8848.95. Now I'll square that denominator. And I get 9.7720. Now, we really only use 3 sig figs and everything. And in fact, yeah, 3 sig figs is about all we can do because we're adding these two. This would be 6,380,000 basically. And that's not really zero. So they're not even really lining up with that too much. But that's meters per second per second. So you can tell if you actually really covered the proper number of sig figs, it's off by 3 in the second decimal place. So 0.03 divided by 9.8 gives you 0.3%. Okay, now let's do G at the deepest spot on Earth. So if I remember correctly, that's supposed to be the Marianas Trench. It's in the Pacific, I know that. So deepest. Well, that turns out to be the deepest depth turns out to be basically 36,161 feet. So when I calculate that, it's 6.67 times 10 to the negative 11th, again, times 5.98. 5.98 times 10 to the 24th over 6.38 times 10 to the 6th minus, now we're going to do, that turns out to be basically 11,021.9 meters, and that's 1 extra sig fig. So when I square that and everything, I'm gonna get 6.67 e to the negative 11 times 5.98 e to the 24 divided by parentheses 6.38 e to the 6 minus 11021.9, and now I'm going to square that denominator, and in this case I get 9.83. 8330 meters per second. So you can tell this one's about again 0.03. This is higher by 0.3% again. So yeah, we don't normally need to worry much about worrying about G changing over the surface of the Earth, because even if you go to the highest place, you're only going to get a 0.3% error. And even if you go to the deepest place, you're only going to get about a 0.3% error. Any questions on that? All right, well, I will go ahead and start on another example, because what you really got to know is you've got to be able to add up gravitational forces. And being a force, we've known for some time that forces are vector quantities. So we need to deal with the vector quality of a gravitational force. I'm really bothered by this being so crooked. This side is crooked compared to the screen, but anyways, I'm going to pretend like it's not there. It's not bothering me. Okay. So what I'm going to do is I'm going to put 3 masses in a formation of an equilateral triangle. So I'm going to say the mass up here, mass here, and mass here. This is going to be M1, and it's going to be equal to 0.16 times 10 to the 9th kilograms. This is going to be M2, and that's going to be 0.16 times 10 to the 9th kilograms. And this is going to be M3, and that's going to be 1 times 10 to the 3rd kilograms. And I'm going to say this equilateral triangle has a characteristic length of 100 meters. In other words, this is 100 meters, that's 100 meters, and that's 100 meters. Now, that also means, of course, that these angles are all 60. So that's, again, some geometry facts you got to know. Equilateral means basically all the angles are the same. The sum of the angles in a triangle is 180. Therefore, if you divide 180 by 3, you get 60. Isosceles triangles, another type, and that's one where two sides are equal, all that kind of stuff. So those are things that you will come across in physics that they expect you to know. So how do we actually add these? Let's say I want to know what is the total force on 3. That's the problem, okay? Well, the force on 3 is actually equal to the force on 3 due to 2 plus the force on 3 due to 1. Okay, and that works for any number of forces. And remember, this nomenclature means on 3 due to 1. In my world, that's the way I'm using it, okay? And I stick to that the whole semester. Not everybody agrees on what way to call that, but that's the way I'm calling it, okay? All right, to do this, what we got to do is just use Newton's law of gravity to calculate the magnitude of the force. So let's start off by calculating the magnitude of F31, say. So the magnitude of F31 is going to be 6.67 times 10 to the negative 11th times the mass 3, which is 1.0 times 10 to the 3rd kilograms. I shouldn't even put units up here. Sorry, I put a kilogram in there. And then the mass of 1 is 0.16 times 10 to the 9 kilograms, since I put it on the other one. Okay. And then the distance between them is going to be 100.0 meters squared. When I do that calculation, that turns out to be 1.07 times 10 to the negative 3rd newtons. And that's why I used the 0.16, because I knew that would cancel out the 6.67. So I was trying to get roughly 1. Okay. Now that's just the magnitude. In order for me to actually calculate that, I need to know its direction, which means I need to find the X and Y component. Well, what I do know is that's the attractive force. So that, and it's between 3 and 1, and it's on 3. So that means the force is right here and points this way. Right? It's attractive, meaning it's pulling M3 towards M1. So I now can say, wait a second, that's the hypotenuse of a right triangle. That's the hypotenuse of a right triangle. And this angle right here is 30 degrees. Everybody sees why that's 30, right? And I'm going to call downward the positive Y direction, and I'm going to go to the right the positive X direction. So this is F31 sub Y. This is just plain F31. And then this is F31 sub X. So I can tell already that F31 sub Y is really just going to be equal to 1.07 times 10 to the negative 3rd newtons times, notice it's touching the angle 30, so it's cosine 30. Consulting my special triangle, I put the 30 up here. I know the 1's across from it, the square root of 3, which is approximately 1.73, and the 2 is here. I can see that, in fact, cosine 30 is adjacent over hypotenuse, which is √3/2. That's 0.866. So I'm going to say this is equal to 0.86 6 times 10 to the negative third newtons. And it's in the positive direction, so I'll put that sign there. It might be a 7 here, but that's an extra digit anyways. We're only using 2 sig figs, so it doesn't matter to me too much. Now this one's going to be 1.07 times 10 to the negative third newtons times the sine of 30 degrees. And in fact, it's going to be negative because I said to the right is the positive x direction. And I know that the sine of 30 is just 1/2. So 1/2 of essentially 1 is 0.5035 times 10 to the negative third newtons. So that actually allows me to write the vector F31 as negative 0.5035 times 10 to the negative third newtons in the I hat direction, plus 0.866 times 10 to the negative third newtons in the j hat direction. Does that make sense to everyone? So there's more than one way you can actually take this magnitude and make it to a vector. One way that always works, is just a little bit more work, but sometimes it keeps you from getting too confused by everything you're doing, is you could take the coordinates, since you want the vector to end here, point this way, I mean, you could take the coordinate of this point minus the coordinate of this point. So let's say x1, y1, z1, and this one would be x3, y3, z3. You could just say, okay, well, there's going to be a vector f3, or let's say a vector r31. And what I mean by that is the vector that basically points the same direction as the force f31. I could just write that as x1 minus x3 I hat plus y1 minus y3 j hat plus z1 minus z3 k hat. That vector would be exactly parallel to that line, and it would point the right way because the last coordinate I used the last coordinate I used was the x1, y1, z1. Okay, so it's that minus that, and that automatically makes us point in the right direction. And then all you have to do is make a unit vector out of it. So you divide it by its magnitude, and then you'd have a vector who has no units, but just points in the right direction. And you can just write it right next to the 1.07 times 10 to the negative third. And as long as you distribute that magnitude to each of the components, that'll work perfectly. So that's another way. It's a little more work. The only time I really suggest you doing that is just you're doing a lot of them, and it's just, you know, getting kind of nerve-wracking and confusing. Then you might want to switch to that. So that's another way you can do it. Just make a unit vector, so on and so forth. But it's always final minus initial. That's why I did x1 minus x3. Final minus initial will get it for you. Now, let's look at this. What we realize is now I need F32. Well, F32, if you write it down, you're going to see it's 6.67 times 10 to the negative 11th times the mass of 3, that's the same, times the mass of 2, which is the same, divided by the distance squared, which is the same. So you can immediately tell that F32 has the same magnitude of F31. So you can automatically say it's going to be 1.07 times 10 to the negative third newtons. So now that we can say that, we don't have to do much work. We also know, for instance, that it's going to point along this line. So again, you got a 30-degree vector, a 30-degree angle, and that's adjacent to the y component. So you see the two y components are both going to add together, but the two x components are going to be identical, just like the two x component, just like two y components were, except the x component for this one's negative and the x component are positive, and the x component for this one was negative. So I can immediately, just using the symmetry of the problem, I can immediately say, oh, okay, well, F32 is just going to have the positive of that component. So I'm going to say positive 0.5035 times 10 to the negative third newtons I hat, but it's going to be exactly the same y component. So I'll say plus 0.866 times 10 to the negative 3 newtons. And that's in the j hat direction. So now I can just say that F3 is equal to, when I add this vector and this vector, notice the x components cancel out. And lo and behold, all I get is 1.848 times 10 to the negative 3 newtons in the j hat direction, which remember we call downward. So that's the total force. I think I can fit all this in one page. There you go. Are y'all able to read it better tonight? Because I connected it with an Ethernet cable instead of using my Wi-Fi, and I'm hoping that took care of a lot of the pixelization that you were getting.
If it's in the downward direction, would it be negative?
It could be, but I chose to make my y direction positive downward. So it's just like, saying G's pointing in the positive direction. You're allowed to do it. It's just a little counterintuitive. But when you do something like that, you got to make sure you have a drawing somewhere so I can see, oh yeah, he's saying down is positive y, so that's fine. Anybody have any questions on that? Can y'all read everything I wrote? All right, so now I'm going to go ahead and give you a robust formula. I usually don't do this in this semester, but I noticed your book did, and I thought maybe this will help you guys next semester, because I know it sort of blows my students away in the 242 course when I do this for the Coulomb force. But I'm thinking maybe if I do it now, you'll have seen it this time and maybe even applied it a couple times. And then when you see it in the 242 course, it'll make a lot more sense. So what I'm going to do is draw a XYZ coordinate system in space now. So this is going to be my y-axis. This is going to be my z-axis. And my x-axis is going to come out of the page. Okay. You have to make sure you make a right-handed coordinate system. See, this is my right hand. See how I'm holding it? Whenever you make a right-handed coordinate system, that means this index finger is the x direction. The middle finger is the y direction. And the thumb is the z direction. All of that has to be done with your right hand. And if it matches, as you can see, it does. If you can turn your arm around like that, if it matches, then everything's fine. If you make a left-handed coordinate system and then you do calculations with it, you're going to get wrong answers, and it takes a lot of math to correct it. So don't do that. Just always make your coordinate system right-handed, and life will be good. What I'm going to do is I'm going to imagine a mass, let's say M1 at this point in space, and I'm going to imagine another mass, M2, at this point in space. Now, what I'm going to say is I'm going to imagine this is my negative x-axis back here. I'm going to say there's a vector pointing to M1. And that's called R1. And really where M1 is if I drop this down and then I run a line parallel to this x-axis, that's the y component. And now if I run a line parallel to the y-axis, then that would be the x component. So you can see it's actually back behind the page, and it's in the vertical direction as far as z goes. Now I can draw another vector, and that's going to be R2 vector. And that's just the vector that points to the point particle M2. Now this one, you might say, is at this point y, and this would be its x coordinate. Okay, so that's me trying to show you in 3 dimensions what the orientation of these vectors are. Okay, now what if I wanted to find f on 1 due to 2? So this means force on 1 due to 2. That's what my terminology means. Okay. Now you've got 2 vectors here. You got R1 and you got R2. Can you tell me how you can use R1 and R2 to make a new vector that points in the direction of F12? Anybody have an idea? So what can you do with R1 and R2 to make a new vector that points in the direction of F12? Now, first off, what is the direction of F12? That's the force on mass 1 due to mass 2. So remember, gravity is always an attractive force. And what that means is, in this case, you got to imagine a line connecting the 2 point masses. And then you got to say the force is pulling it towards that other mass. So that's the direction. It seems like the direction goes from the head of R1 to the head of R2. Can anybody think of a vector that points from the head of R1 to the head of R2? Someone says subtract them or add them. So if we did addition, we'd have to complete the parallelogram because these 2 vectors are tail to tail. So that would actually be something like this, and that vector would point all the way over there. So the addition can't be right. What about the subtraction? How would you do that? Well, you could try R1 minus R2. I wrote minus 2 instead of R2. Okay. Well, the definition of subtraction is R1 plus the opposite of R2. Well, if I took the opposite of R2, that means the head's going to be down at this end, and now they're head to tail. So that would go from here to there, which is the opposite direction. So the subtraction is a good idea. It's certainly parallel to the line we wanted. So what we want to do, though, is do R2 minus R1, which I'm going to call R21. Okay. Notice it keeps the same order, so it's not a hard thing to remember. That's going to be R2 plus the opposite of R1, which means you're going to take this R1 and put the head down here, and now they're head to tail. So head to tail, you go from the tail of the first to the head of the last. That points in exactly the right way. Okay, but notice this, the subscripts are in the opposite order of F12. So that's kind of weird, and it makes it kind of ugly. So instead, what I'll do is I'll say F12 is equal to negative G M1 M2 over R12 squared times R12, because the negative of R12 is R21, which is really what I wanted to use. So I can do that. Now here's the problem with that. By multiplying this, which is exactly the right magnitude, by R12, I've made this essentially G M1 M2 over R12 to the first power. So in order to account for that, I need to change this to a third power. Okay. So now everything's in the same order, R12, R12, F12, all that good stuff. And that's a good working vector definition. It's still a 1 over r squared law. It's just because R12 has a magnitude. If I wanted to not make that third, I could have said equals negative G M1 M2 times R12 hat over R12 squared. That would work fine as well. But of course, you then have to find the R hat, which is literally taking this vector and dividing by its magnitude, which is the same thing as putting R12 cubed there. Any questions on that? That red does not show up in writing very well. It's okay for symbols and vectors, but it's not very, it doesn't seem very clear there. All right, well, I think that's good enough for today. We've got a couple other little things we're going to do in chapter 5, but that's essentially it. I think you can make sense of it. I'm going to talk about relativity a little bit next time, so you'll have an idea what Einstein did to quote unquote correct gravity. Okay. In some sense, Newton's laws are still right. Newton's law of gravity is still right. For instance, you can still go to the moon or you can get to Mars with Newtonian physics. You don't actually have to use relativity to make your orbit proper to get to Mars or to get to Jupiter or anything like that. That being said, your clocks would be off if you didn't use relativity, because it turns out there is a significant difference in the time, and our time's measured so accurately in space via satellites and stuff that we have to do. We do have to correct for general relativity in those cases, but the mechanics would work just fine. We could still get to the planet, land where we wanted to, and all that good stuff. So if anybody has any questions, please stick around. Otherwise, you guys are free to go. Thank you for coming, everybody. Jared, you want to share that lab question now?
Sure. So it's on the error propagation lab.
Okay. Do you need to share a screen or anything?
I can if you'd like. It
Yeah,
might be easier.
I just made it available for you to do that if you'd like.
Okay. I have my answers up already typed in. Is that okay if I show it?
Yeah, that's fine. I'll be able to tell if someone turns in something where they didn't really do the work. So.
Okay. So this is what I have. When I was trying to prove or, show that the error or the standard error of the function is equal to this, I got this extra little bit on the end, which I had to basically assume there's a constant here that's equal to 0 to actually make this work.
Okay. The formula up at top says, yeah, can you show me that formula? There you go. Just want to make sure I didn't have a typo or anything. The very
this one?
top, yeah, that's the one variable one. Isn't there another one on here where it says that go to the very top of that page? Yeah, okay, scroll down just slowly so I can see. I might have erased it by accident. That might be what happened.
Yeah, because I couldn't figure out how to make it work.
Yeah, that's what it is. Yeah, you've got to get the formula from the video because I didn't put it there. Keep on going down. Let me see. I'll show you the formula in a second. I'll write it up here. It's not a big deal. But okay, yeah, that's what happened. I left it off here because I was making y'all watch the video. So the real formula, it turns out, when you have functions of many variables, let me steal the screen from you for just a second. And this will explain why you got what you got too. So the real formula is the uncertainty in F is equal to the sum of the squares of the partial derivative of f with respect to x times the uncertainty in x plus the partial of f with respect to y squared times the uncertainty in y squared plus the partial of f with respect to z squared times the uncertainty in z squared plus dot, 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 however many other variables you have.
Mm-hmm.
So when you have f of x, y, that's only two variables equals x plus y, right? Then the partial, what we mean by partial, you haven't learned this yet, but that's why I showed it to you in the video. The partial f with respect to x means, let's pretend the y, since that's the only variable, let's pretend that's a 4.
Yeah, I'm in diffEQ and I've done partial derivatives
Okay, gotcha.
before.
So you know the
Yeah.
answer to this is just 1.
Yeah.
Okay.
Mhm.
And then the partial of f with respect to y is also just 1. So in this case, you get the uncertainty in f is just 1 sigma x squared plus 1 sigma y squared square root, which is exactly what you're trying to show. And if you want to do something ugly, like let's do xy. So f of x equals xy. The partial of f with respect to x is just y. And the partial of f with respect to y is just x. So the uncertainty in f is equal to the square root of y squared partial x squared plus x squared partial, or uncertainty in y squared, like that. Now, I said in this case, you're supposed to prove the fractional error. So if I do sigma f over f, what that means is I'm literally just going to take this uncertainty and divide it by the actual function.
Mm-hmm.
So y squared sigma x squared plus x squared sigma y squared over, now the function is just x times y. But if I want that to be inside the square root, then I need to square it. And I can put the square root under there. And now it's all under the square root. And you can see I'd get y squared sigma x squared over x squared y squared plus x squared sigma y squared over x squared y squared. You can see that in this case, the y's cancel out. In this case, the x's cancel out. And you get instead the square root fractional uncertainty in x squared plus the fractional uncertainty in y squared, QED.
Okay, gotcha. I guess I just figured that I had to start from the sigma f equals df over dx.
Right. Yeah.
Sigma x and just start from there and go.
Yeah, that's why I told everybody to watch that video, because that's where I explained that. Luckily, I'd said that, but it doesn't help that I didn't put the formula in there. If I'd put the formula in there, you probably would have figured it out anyways. But you understand that now? That's a lot more straightforward, right?
Yeah, you said the it was in the video.
Yeah, I said you're supposed to watch a YouTube video, and I gave a link to it.
Yeah, I don't know if I just missed it or something, but I can't find any like calculus portions or any like written calculus portions.
Okay, let me find it right quick on the page.
I can put it in chat if you'd like. I have it pulled up.
Okay, yeah, do that for me.
Mm-hmm.
There's one when sig figs fail. That's not the right one. It should be the error propagation formula, but I might have given you the link to the wrong video. Who knows?
Yeah, this is the link to the video you put in the announcement for error propagation.
Okay. Let's see which video this pops up.
And I think this video is similar to the sig fig lecture you gave on like week 1 or
Yeah,
like the first or second lecture or
so
something?
that might be a complete crap then. Let me see what comes up. It's just taking a little while to
Mhm.
load. Yeah, this was supposed to be the one. Let's see. Yeah, probably. I think I did send you the wrong video.
Okay.
Look what this looks like. Yeah, I'm just quickly looking at it to see if I finished up at the end showing you. That's just a sig fig one. Yeah, you're right. Sorry about that. Yeah, I'm glad you let me know that because clearly I gave everybody a wrong. I'm going to give everybody another week to do this, and I need to find the right video and give them that one. But at least they can see this. They'll see what I just did. But that is the formula you need to use. I don't know where that video is now. Oh well, I'll find the video. I will get another link and put that up. Y'all have at least another week to do this assignment, so don't stress out if you don't feel like you know what's going on right now.
Mm-hmm.
But yeah, this is the general rule. You're just going to take the derivative of whatever the function is with respect to each of the individual variables. You're going to square it, multiply it by the uncertainty in that variable squared. And technically it's done at that point. It's just, it turns out if the things are multiplying or dividing, the fractional errors just add like the sum of the squares. Right? So
Yeah.
the fractional error equals the squares of the fractional errors added up and taking the square root. That's when you're doing multiplication or division. When you're doing adding or subtracting, it's the same formula, except you're using the regular error instead of the fractional error.
Mm-hmm.
So it's just a neat little thing, but you can tell it gets really messy. And it's a lot of work to do when you're actually doing a lab that way, but that's really is the way you're supposed to be doing labs. And in fact, we're going to start, I'm trying to get the department to start doing that immediately on all labs.
Okay.
So it probably won't start till next semester, but
yeah. I just had one last question.
okay.
Same lab.
Okay.
I can share my screen again real quick.
Yes.
It was on this last question, which says to use the following data for the dimensions of a rectangular solid.
Mm-hmm.
And it asks us for the best estimate of the volume of the solid, which I figure is just these multiplied together.
Exactly.
And then
it shows you if I gave you the right one. All right.
Yeah. Yeah. And then the standard deviation.
Mm-hmm.
But the standard deviation, which is this formula, requires n, which is the amount of samples, basically.
Right.
And the samples are never given. And then we can calculate the standard error from, all of this sigma stuff up here.
Gotcha. Okay. I thought this was
so
are these the same numbers that were in the one above? This was supposed to be tied to the data above. That was the way you're supposed to get the digits, but that looks just like H now. Okay, yeah, I see.
Yeah, this is just H.
Good. That was another good catch, by the way. So yeah, I think what happened was I cut and pasted and took some of the wrong stuff. Yeah. So yeah, you're not able right now to do that number 9. So I'm going to have to address that and like I said, give everybody an extension and then address that or throw that question out, one of the two. But yeah, you're exactly right. That was intended to refer to the data that I'd already given you. But I think when I erased some of the data when I was making it for my non-calculus class, I think I accidentally erased some of the stuff that y'all were supposed to get. So that's the same reason the formula is not there. So yeah, thanks for catching that. That's the danger of making something at the last minute when I finally got to have a meeting.
Yeah.
But my fault, man. Sorry about that.
It's all good.
Thanks for catching it though for me.
So should I just wait until you correct this to turn it in, or
yeah,
should I just strike
do
it
the other
out?
parts that you can do, and just wait for number 9. Like I said, I think I've given you enough to know what to do now. So you can do I suspect you can do everything but number 9 now. But if you can't, that's okay. Just you got another week. But I'd say knock it out while you can. since you probably got it fresh in your head now, you can probably do the rest of it pretty straightforward.
Oh yeah, I'm finished with all of this.
Good deal.
That's the last thing that I needed to do.
Gotcha. No problem. I'll either correct that or throw that question out. So thanks for asking me those.
Okay. And if I turn these proofs in, would this be okay to turn in?
Not this one, not that one, just because it's done with the that extra term that would come from not doing partial derivatives.
Well, this is from partial derivatives. I got this constant.
Okay,
I
gotcha.
can bring it up. I looked up on Wikipedia for error propagation.
Mhm.
And if you multiply two error terms together, so like the sigma x, sigma y,
Mhm.
you get you can basically concatenate it into basically sigma xy like
Yeah,
this.
right.
But when you do that, let me reshare my screen so you can actually see. You get this extra factor of rho. If I can pull it up here, you get this extra factor of rho.
Right.
You can see here.
The covariance.
Yeah. So that's basically what I was basing this K off of, was the assumption that rho is equal to 0.
Yeah, I think this is coming from them doing a square of a function as opposed to a sum of squares. You get what I'm saying? Like, you should never get cross terms when you're doing this, in other words.
Okay.
So yeah, that's just, you were trying to fish out what I left out and ended up finding something that works in some scenario. It just doesn't happen to be valid in this particular scenario. But yeah, you actually found some of the fundamental stuff regarding partial derivatives. You might, since you're in differential equations, that's basically where you get exact differential equations. Where you take the derivative of m with respect to y, and then you take the derivative of m with respect to x, and if those two are equal, then you know it's an exact differential equation. That's what you're looking at now. Stuff related to that. Okay. All right. Sorry about that, man. Matthew, did you have a question? You might not even be here. Well, if you don't have anything else, I'll let you go then.
All right. So I'll just redo these proofs.
Yeah, and you don't need to typeset them. If I mean, I like that it is. It looks really good when it's typesetted, but I'd rather see the various steps handwritten than skip steps typeset, just because typeset one is awesome looking, it's easy to read, but it can also be used to fudge a lot of steps. That's why textbook authors leave so many steps out. It's because it's a pain in the butt to typeset.
Oh yeah. I do a lot of coding and stuff, so
Oh yeah, you look like you're
I'm
using actual straight LaTeX instead of the word palette, basically.
I've just kind of figured out all the shortcuts, so typing all of this out isn't very difficult.
Yeah, that's called LaTeX. It's a language you can learn, and it's if you have the right type of editor, you just type it in real time, and it's lightning fast, which you've got.
Oh yeah. Yeah.
All right. Well, have a good one, man.
All right. See ya. Thank you.
You're welcome.